So apparently one of the problems, the second problem on the homework that I assigned, requires you to use Simpson's rule. I didn't intend for that, but since I did it, let me review Simpson's rule. Or what to do if the integral is not on Wolfram alpha. So here's a function, and I'm going to just draw something crazy like that you're going to have to integrate. And it's not on Wolfram alpha. And so what do you do? So you can't find it in any book, or it's not on Wolfram alpha. You're going to have to integrate this numerically. So what we're going to do, one way to do it, it's easier than Simpson's rule. It's not the smartest way to do it, is you break your integral. Remember, the integral is just the area. So you break the integral up into tiny little pieces like this. Okay, so I'm going to do about that many. And we want to get that area, but we can't do the integration, so we're going to approximate it with some rectangles. So I'm going to draw these rectangles like that. There we go. And you can calculate the area of a rectangle, right? So you just get base times height, and you do this over and over, and you just add it up. And that will give you an approximation to the area. So obviously you would do something like this on Excel. But then you're going to say, but it's wrong. Look, there's all this area that you're adding up that's not in there. Or you're missing this one, you're missing that. You got extra there. And it's not going to average out. It'll be off. What you can do to make the error less, without having to use Simpson rule, is to make your rectangles smaller and smaller. So if you use small enough rectangles, the error will be very small. And you have Excel, so it really doesn't matter. That's what I do. I just use the rectangle rule, and I just make the increments here, the delta x, very small, and I know it'll be pretty accurate. But it did say to use Simpson's rule, and so why don't we do that? And so Simpson's rule, okay, is just this. We know that the rectangles are off because it's curved, but the rectangles are not. You know, it's a rectangle. So what we're worried about is this. It's like that rectangle is clearly like almost double the area of that's actually under the curve. So Simpson's rule is just this. You take these 3 points at the left end, right end, and in the middle, and then you fit in your best fit parabola. And see, that's pretty close. And then you integrate the area under that parabola. So you get these 3 points. You find the parabola that goes through those 3 points. And then you get this area. And then you add them up. Well, what is the area under the 3 points? And how do you get the parabola that goes through those 3 points? You should have derived this in your calculus class, but if not, here is Simpson's rule. So for any distance, let's call this from A to B, and let's call that delta x, where you're going to have the point right in the middle, and so you have, I'm going to call it the function at the left, the function at the right, and the function in the middle. This area here, under the parabola, which is pretty close to the real area, the area, according to Simpson's rule, is delta x over 6. Okay, so the base over 6 times the function on the left plus 4 of the function in the middle. Oops, 4 of the function in the middle. I'm going to erase that. Sorry. 4 of the function in the middle plus the function in the right. Or how I like to think of this is delta x times left, 4 middle, and right over 6. So in a way, you see this thing here? That's like kind of like the average height. 1 of the left, 1 of the right, 4 in the middle divided by 6. And that's the average height times the length, delta x. This is Simpson's rule. What I'm going to do is I'm going to do an example where we know the exact area. And then I'm going to do it in a spreadsheet using rectangles and using Simpson's rule. Okay, so the example I'm going to do is I'm going to try and integrate some kind of like x cubed plus x squared plus x plus a constant. And we're going to integrate that, let's say, from 0 to 10 or something like that. If I just did a parabola, Simpson's rule will give you the exact answer because it's a parabola. So I'm going to use a cubic just so it'll be a little off. And we'll see which is better. Well, Simpson's rule is better. But we'll see how much error there is in using a rectangle versus using Simpson's rule. So I'm going to go make that spreadsheet and come back. So here's a cubic function I made up that I'm going to integrate from 0 to 10. I plotted it in Excel since I had it there for Simpson's rule anyway. So the integral of 0 to 10 f of x is 1/4 x to the 4th minus 10/3 x cubed plus 7/2 x squared plus 50x from 0 to 10. And that equals 16.67. There's a lot of positive and negative areas that seem to be canceling each other out there. Okay, so I'm going to fix my spreadsheet up, do this both by rectangles and parabolas using Simpson's rule, and we'll see how it turns out. Okay, so using the points shown here, the dots, when I did using rectangles, when I got the area using rectangles, I got 25.9 versus 16.67. And then when I use Simpson's rule, and so I'd have to take every other point because you need 3 points for Simpson's rule. Drum roll. I got 16.67. So yeah, I have to agree that using Simpson's rule is a lot better, but it involved a little bit of working because you have to use every other point, and so it's a little hard in Excel. Okay, so that's Simpson's rule. I am posting these notes as well as the spreadsheets I made to do this. Okay. Oh, and a quick addendum to the spreadsheet. So what I went ahead and did was I did 3 integral techniques. And so let's say this is your interval. So the rectangle one, which I talked about, and I did the Simpson's rule, which I put the parabola, and then I added another one, the trapezoid rule, where you just make a straight line between those 2 points and you get that. And obviously the more complicated the curve, usually the better the results. And so this said 25.9. This one, the integral, came out to 17.2, and this integral, it came out to 16.7. Now, you can make any of these be very accurate by just taking a very small delta x. Okay, that's all for now, and I'll go ahead and post these.